Okay, so here we are. Calculator may not be used. So we're going to do all of these problems relating to related rates and motion. So number one, we're going to cruise right along here. Particle is moving along the x-axis. The position of the particle is given by this expression here, this equation, 6t minus t squared. The total distance traveled by the particle. Now, in order to do this problem, we need to know when the velocity is zero, because that's going to help us know when and if the particle changes directions at any time. So the first thing that I'm going to do is I'm going to take the derivative of the position equation, which will give us our velocity equation. So the derivative of that is just 6 minus 2t. And we're going to set that equal to 0. And so we're going to have 6 minus 2t. And we're going to have negative 6 equals 2t. So negative 2t. So t is going to equal 3. Now, how does that help us out? Well, if you take a look at your velocity, and we've got our time number line here, it says that time starts at t0 and ends at t5. So we're going to go from 0 to 5 on the timeline. And we've got t equals 3 here, where we know the velocity equals 0. And in between 0 and 3, I'm going to plug in a number into my velocity equation. So let's try v of 1. And here's my velocity equation, just a reminder. So v of 1 is going to be 6 minus 2. So that's a positive number. And we're going to plug in something like 4. And when I do that, 6 minus 8, that's a negative number. So remember what that means. Your particle is going to be moving to the right when velocity is positive, stopped when velocity is 0, and moving left when the velocity is negative. Okay, so what that basically means is if I set up a position chart, not with x, with time and our position, and we start off at time 0, from 0 until 3, the particle is moving to the right. Well, what is the position? Now we're going to go back and we're going to use our position equation. That was this guy. So our position at time equals 0, if you plug in t as 0, it's just going to give you 0. If you plug in t equals 3, right, we can do some number crunching off to the side. X of 3 is going to equal 6 times 3 minus 3 squared, 18 minus 9, so that's 9. And time ends on this problem at 5, so the position at 5. So 6 times 5 minus 5 squared, so 30 minus 5 is just going to be 25. Let me try that again. 30 minus 25 is 5. Yikes. It's been a day, guys. It's been a day. So basically what we know is that this entire time the particle is moving to the right. And this entire time the particle is moving to the left. So if I just look at the change in position during those times and add up the difference, that will tell me how far this thing moved. So it moved 9 units to the right, and then it moved 4 units to the left. So overall, it moved a total of 13 units. The position of a particle moving along the x-axis is given by the position equation. What is the acceleration of the particle? Well, velocity is the first derivative, so we're going to go ahead and take the first derivative of this thing. Derivative of sine of t is cosine of t. And the derivative of cosine of t is negative sine of t. And simplify that just a little bit. Cosine of t plus sine of t. And now we can go ahead and do the second derivative, which is just the derivative of velocity. So the derivative of cosine of t is negative sine of t. Derivative of sine of t is cosine of t. So we're looking for the acceleration at 3 pi over 4. All right, unit circle lovers, 3 pi over 4. This is 0 radians and a coordinate point of 1, 0. This is pi radians with a coordinate of -1, 0. So there's 1 pi over 4, 2 pi over 4, 3 pi over 4 is right here. And this corresponds to -2 rad 2 and +2 rad. Oh my gosh, I can't even talk. Rad 2 over 2. So the sign is the y value. And so I know that the sign of 3 pi over 4 is going to be rad 2 over 2, but we have that negative from in front. So negative rad 2 over 2 plus the cosine is just the x value on the unit circle. That's this one. So that's going to be a negative rad 2 over 2. Add those two guys together because they have a common denominator. -1 rad 2 plus another negative rad 2 is -2 rad 2 over 2, and your 2's will cancel. So your final answer is just negative rad 2. And number 3, particle's position is given by this equation. At what time is the particle at rest? Particle is at rest when v of t equals 0. So let's go ahead and take the derivative of this thing. 3t squared minus 24t plus 36, and we're going to set it equal to 0. I can factor out a 3. And we're going to go ahead and factor even further. Minus 6 and t minus 2. Wow, computer's going crazy. So this is giving us a t value of 6 and a t value of 2. Number 4, the radius of the circle is increasing. So at a certain instant, the rate of increase in the area is equal to twice the rate of increase in its circumference. What is the radius of the circle at that instant? Now, because I have done problems like this before, I know where to go with this and what to do. It's just a matter of having enough repetition and practice. But I'm going to approach this as a novice. Like, what would you guys think as you're looking at this problem? So we're going to write down all of our information first. The radius of the circle is increasing. Okay, so that means r is changing. So think about it. We've got a circle, and there's your radius. The rate of increase in the area, dA dt, is numerically equal to twice the rate of the circumference. What is the radius of the circle at that instant? Now, obviously, we are going to have an area equation, and we're probably going to have a circumference equation. So let's go ahead and do an area equation first. Area of a circle is just pi r squared. If I was to do the derivative of this equation with respect to time, I would have dA dt equals 2 pi r times dr dt. Well, that's good because I'm looking for the radius. And it shows up here, so that's good. I've got a little bit of a problem, though. I don't know what dr dt is. So I'm just going to keep on cruising along here. They give us information about the circumference, so let's maybe try the circumference. So circumference equals 2 pi r. Well, let's go ahead and take the derivative of that with respect to time. So dc dt is going to equal 2 pi dr dt. I can do something with this because I see dr dt is showing up. So dr dt, here's dr dt. Let's go ahead and solve dr dt. So dr dt is going to equal dc dt, and I'm going to multiply by the reciprocal of 2 pi It's the same as dividing. It's just I don't want a dc dt over a 2 pi. Just it's too many divisions. So I'm going to take this and replace it into my dr dt. So I've got dA dt is going to equal 2 times pi times r. Remember, that's what I'm looking for. That's good. And then times dc dt times 1 over 2 pi. Now let's see if that helps us out at all. I know it's kind of going back and forth all over the place. 2 pi's are going to cancel. And I still have a little bit too many variables in here, but I'm going to go back up to the top and I'm going to take a look. I am told that dA dt is equal to 2 dc dt. All right, well, let's go ahead and replace dA dt with 2 dc dt and see if that helps us out. And that works out really nice. So if you didn't see where that came from, let me go ahead and use my highlighter. I'll change the colors on it. So dA dt is just twice dc dt. So I replaced the dA dt with that value. Now the reason this works out nicely for us is take a look at what happens when I divide both sides by dc dt. They're gone. And I'm left with my r value of 2. Problem number 5. The graph of the velocity. Make a note. Anytime you're given a graph, exactly what is that graph? On which of the following intervals is the particle moving to the left? Use your helper sentence. Particle is moving to the left when what? Well, when v of t is less than 0. Now take a look at what you're given. We are given the velocity graph. So we're looking for where this thing is less than 0, meaning below the x-axis. So that's this region and this region. So look at those time intervals. We're talking from 0 to 2 and from 4 to 6. The radius and height of a right circular cylinder are changing at the respective rates of 2 inches per second and 3 inches per second. So let's go ahead and label these. It says respective, which means in the same order that the problem was given. So we were given radius first, so this is the rate of the radius. So this is dr dt. And this is going to be dH dt. Problem number 1 is, or problem A is asking what rate is the volume changing? So I'm looking for dV dt. I have a lovely little keyword here, when, which means I don't plug this in until after the derivative. R is 4, H is 2, and I'm told what the volume of a cylinder is. Remember, with any free response, you have to label which part of the problem you are answering. No labels means no credit. So volume is just going to be pi r squared h. So let's go ahead. I don't have anything else to, I could draw this out, but my height is changing. My radius is changing, so it's not like I can plug any numbers in yet. So let's go ahead and take the derivative of this thing with respect to time. Let me move this over just a little bit. So derivative with respect to time. So that's going to be dV dt equals pi times, and now we're going to do our product rule. 2r, let me do it in the same order. First times the derivative of the second, plus the second times the derivative of the first. And now we're going to evaluate this thing because we want dV dt when r is 4 and h is 2. That's going to be 4 squared times dH dt, which was 3, plus h, which is 2, times r, which is 4, times dr dt, which is 2. Now, if this was a free response problem, you just need to add units and you're done. But we're going to go ahead and simplify this just because it's good practice, to be honest. 4 squared is 16. 16 times 3 is 48. So I'm going to have pi on the outside. 48 plus 2 times 2 times 2 is 8. 8 times 4 is 32. So this is giving us 80. Get out of there, little guy. Here we go. 80 pi. Volume is measured in inches cubed, and time is measured in seconds. For part B, same kind of a problem, except now we just have the formula for area of a cylinder, the surface area. I've seen books and other people use SA for surface area. I think it just adds an element of confusion, so I'm just going to say A equals 2 pi r h plus 2 pi r squared. Okay, derivative of that with respect to time is going to be dA dt equals, now we got to do a product rule in here. We got 2 pi r. So first times the derivative of the second plus the second times the derivative of the first. Derivative of 2 pi r is just 2 pi dr dt. And now we have to do the derivative of 2 pi r squared. So it's just going to be 2 pi times 2r dr dt. And we want this thing, when we're evaluating it, again at r equals 4 and h equals 2. 2 pi times 4 dh dt was 3 plus h, which is 2, times 2 pi dr dt, which was 2, plus 2 pi times 2 times r, which is 4, times dr dt, which is 2. Woo, good times. That first little chunk, I'm going to have 24 pi. Second little chunk, I'm going to have 8 pi. Third little chunk, I'm going to have, 32 pi. So overall 64 pi. And that is inches squared per second because it is area. All right, for this next chunk of problems, we're allowed to use a calculator. It doesn't always require it, but we can definitely use it. Particles moving such that the velocity is given by the velocity equation shown. What is the acceleration of the particle when t equals 3? First thing I'm going to do is I'm going to take the derivative because that's how acceleration and velocity are related. So a of t equals 2. Nope, we're doing the derivative. There we go. Derivative of 2 is 0. Derivative of 2.5 times the sine of 0.6t. So 2.5 is a constant multiple. The derivative of the sine of anything is the cosine of that thing. And then we have a chain, so we're going to multiply by the derivative of the inside, so it's 0.6. And we are trying to do this when t equals 3. All right, so my memory is really bad, but we're going to bounce back and forth now. So make sure you're in radian mode. So 2.5, let me go back over here to my calculator page. 2.5 times the cosine, I think it was 0.6 times 3, and then times 0.6 on the outside. And you're going to round to 3 decimal places, so negative 0.341. Number 2, if a circle's radius is increasing at a constant rate of 0.3 meters per second, so that's dr dt, what is the rate of change of the area of the circle? That's dA dt. When the circle circumference is 6 pi meters. All right, so there's a little goofy stuff going on in here. We've got area and circumference kind of mixed in. You've seen that before. So let's go ahead and do the area equation first. Area of a circle is pi r squared. And since I know the radius is changing and the area is changing, we're going to just leave the variables alone. But we are going to do the derivative of this with respect to time. So I'm going to have dA dt equals 2 pi r dr dt. Now I know what dr dt is. And I'm trying to solve for dA dt. So that means the only thing I don't know is my r. But they told us information about the circumference. So they said, evaluate this when the circumference is 6. So I'm actually going to do a little aside here and say circumference is 2 pi r. And I know that at this particular point in time, the circumference is 6 pi. And so therefore, if I divide both sides by 2 pi, I'm going to get my r value is 3. So I want to know dA dt when the r value is 3. And I know my dr dt is 0.3. All right, when you do this out, you're going to get 1.8 pi, and area is measured in meters squared, and time is measured in seconds. In the triangle shown, we've got theta increasing at a rate of 15 over 26 radians per minute. So this is our d theta dt. And you'll notice in the diagram that we have the bottom of this triangle right here, the base of this thing is 10. And it's not changing, which is why it's labeled with a 10. Otherwise, they would have to put a variable in there. At what rate is the area of the triangle increasing? So we're looking for our dA dt. When h is 24. All right, so how do we come up with a relationship for this kind of a thing? Well, we've got a triangle, we've got a theta, and I've got two sides of the triangle. So for this particular problem, I'm going to go ahead and use a tangent expression. I know that the tangent of the angle is going to be our opposite over our adjacent. And the problem with this is that's going to give me a d theta dt, definitely, but it's certainly not going to give me anything having to do with the area. So we're going to be dealing with two equations in this case. So it doesn't matter which piece you work with first. I'm going to go ahead and write an area equation over here. Area is 1/2 your base, which is 10, times your height, which is h. H is changing. So if we were to do the derivative of this guy, I'm actually debating right now if I want to do a substitution and get rid of the h and use a theta instead. I think most of you would probably have done this, so I'm going to stick with this. And by the way, that was 5 times h. So the derivative of 5h is just going to be 5 dh dt. Okay. So the reason I left it is because I think most of you would have probably done that. I'm going to come over here and actually move this guy. I'm going to move this over here so it's a little easier to work with. If I take the derivative of this guy, derivative of tangent of theta is going to be secant squared of theta, d theta dt. And the derivative of h over 10, just remember h over 10 is the same exact thing as 1/10 times h. So the derivative of that would just be 1/10 dh dt. All right, so I can solve for my dh dt. It's just going to be 10 times the secant squared of theta d theta dt. All right, now how does that help me? Well, I can take that dHdt and I can substitute that entire value up in here, because now I'm going to have dA dt, and I'm going to have it in terms of only the thetas. So let's go ahead and do that. dA dt is going to give us 5 times 10 secant squared of theta. We'll get to that in just a second, d theta dt. I need to know what my theta is. Well, it says when h is 24 units. So use this little secondary equation and solve for theta. So tangent of theta is equal to h, which in this case right now is 24 over 10. So that means that theta is going to equal an inverse tan. If you want to reduce that to 12 over 5, you absolutely can. And now you can substitute that in. So our dA dt evaluated when h is 24 is going to be equal to, I'm going to go ahead and multiply the 5 times the 10. So I'm going to have 50 secant squared of, now this looks gross, but you've got calculator, so it's okay, times d theta dt, which I know. D theta dt is 15 over 26. Okay, so now you just have to type that mess in onto your calculator. Friendly reminder, secant squared. I erased that too, and I'm going to put it on the outside because that's what secant squared really means. Okay, so how good is my memory? Not great, so let's try this out. We're going to have 50 times the secant, and I'm actually going to go before that, and I'm going to put in another set of parentheses, and I'm going to put my square in there before I forget. Okay, what was I taking the secant of? I was taking the secant of the inverse tan. My computer's going freaky. Quit. There we go. Of the inverse tan. I think it was 5 over 12, but let's just double check. Nope, 12 over 5. See, this is why we check. 12 over 5. And then times 15 over 26. And all that stuff gives us 195. For a particle moving along the x-axis, we have the velocity of the particle given at any time. The particle is at a position x equals -2 and time equals 0. When is the particle moving to the left? Write yourself a helper sentence. It becomes part of your justification. The particle is moving left when v of t is less than 0. Okay. We have our calculator, so let's go ahead and graph this thing. Cosine of pi over 6 times t. Please, again, make sure you're in radian mode. So cosine, I don't know why my computer does this. It's really fun. So cosine of pi over 6 times t. Now, our calculator uses x's, so I'm going to use an x. Don't want to confuse it by putting in a variable that it doesn't understand, because this is f1 of x, so be consistent. And that's it, cosine of pi over 6 times t. So I'm going to go ahead and graph that guy. And we'll move it over a little bit. Now you can see that it definitely has 2 zeros. It looks like it's at 3 and at 9, but let's just confirm that by going to menu and graph trace, and I'll type in 3, and it confirms that that's a definite 0. I'll type in a 9, that's another 0. So I have In between 3 and 9, right in this region, v of t, which is what we graphed, v of t is negative. So this whole region in here, the particle would be moving to the left. Now, pay attention. This time region ends at 12. So even though the graph continues and goes negative in other places, you got to make sure you're watching for where the graph ends. So this was 9, 10, 11, 12. So the graph actually ends here, so I don't have to be concerned about all this other stuff. Okay? So 3 and 9 in between those two regions. So v of t is less than 0 for, not 0, I literally just said 3. 3 less than t less than 9. All right, part B. Find the acceleration of the particle. That's just the derivative. A of t is just v prime of t. And that's just negative sine of pi over 6 times t. And don't forget that this is a chain rule, so times pi over 6. And it says, is the speed of the particle increasing, decreasing, or neither at time equals 4? You need to know the signs, S-I-G-N, signs of acceleration and velocity, and compare them. If they're the same, the particle is speeding up. If they are opposite, they are decreasing. So let's do v of 4 first. So you can get that right from your graph. V of 4. So you can go menu, you can trace this guy, and type in 4. And you're going to get negative 1/2. And for A of 4, you can plug in the value of 4 right into your equation that we just had. Okay, it actually doesn't even matter what the value is as far as like quantity wise. We just need to know if it's positive or negative. But again, I've got my calculator, but this is just ends up being sine of 2 pi over 3 times pi over 6. The sine of 2 pi over 3 is a positive value. That's what, y is positive up there. There's 2 pi over 3 right here. So this coordinate point is negative 1/2 rad 3 over 2. So the y value for that is rad 3 over 2, but don't forget about that little negative there. So this is negative rad 3 over 2 times pi over 6. Again, you could plug all that into your calculator and you'll get the right answer. It's negative root 3. I should put the pi in front. Negative pi times root 3 all over 12. But it's a negative. That's what we're coming down to. So here's your justification. Since v of 4 and a of 4 are both negative, particles' speed is increasing. Okay. And last but not least, we've got a water tank that has the shape of an inverted circular cone with the tip down. The base radius is 2 meters. The height of this cone is 4 meters. And water is being pumped into the tank. So we're going to have water kind of filling this tank up. And I hope you can start to get the gist of this. We've got similar triangles in here. The water is rising, and so we're going to use the idea of the similar triangles here. So I'll just draw it without the cone, just so you can kind of get an idea. 2, 4, and then I'll call this radius and this height, and that's for just the water. If the water is being pumped into the tank at a rate of 2 cubic meters per minute, that's my dV dt. Find the rate at which the water level is rising. So rate for the water level, it's talking about dH dt according to my diagram, the water level rate. And it says when the water is 3 meters deep. Okay, so that's our evaluation piece, which we'll get to. So if I first take a look, the volume of a cone, 1/3 pi r squared h. I'm going to note again that if I take the derivative of this thing and use product rule, I'm going to have an r, a dH dt, an h, and a dr dt, which I don't have information for. So let's make a secondary equation. We're going to use the cone and the similar triangles. The base of the cone is to the height of the cone as the radius of the water is to the height of the water. Now you're trying to end up with a dH dt, which means you want to get rid of your r's in that primary equation. So let's solve for r. I'm going to multiply my h to the other side. I'm going to have 2/4 h equals r, or in this case 1/2 h equals your r. And that's what you're going to plug in for right here. So v equals 1/3 pi times 1/2 h times another h. And by the time you clean all this up, it's going to be, excuse me, I forgot my square. Sometimes I do that. 1/2 when you square it is 1/4. 1/4 times 3 is 1/12. So pi over 12 is the constant. And that's going to be h squared times another h, which is h cubed. Now we can do the derivative of this thing with respect to time. dv dt is going to equal pi over 12 times 3h squared dh dt. We are evaluating this thing when the height of the water is 3 meters deep. So pi over 12 times 3 squared times our dH dt, which was what we are looking for. Look what I forgot to do. I forgot to plug in for dv dt. I'm so silly. dv dt is 2. I was trying to figure out why we had so many variables. All right, so we're going to have 2 equals 3 times 3 squared. So that's 9 times 3, so 27 pi over 12 is our dH dt when h equals 3. So to solve for that, I'm going to multiply by the reciprocal. So I'm going to have 24 over 27 pi. Again, you've got the calculator for this, so if you want to do all this on your calculator so it's a little bit easier, that's totally fine. But this is 8 over 9 pi, and h is measured in meters, and the water level time is rising in minutes, so meters per minute.